You might be asking, what do we mean by implicit differentiation? Before I explain that process, I'd like to talk to you a little bit about what we mean between the difference between explicit functions of x and implicit functions of x. Let's take a look at an example. Explicit functions of x. Notice here's one format. F of x, we're used to that notation, equals 5x cubed plus 9x minus 3. Another explicit function of x is y equals 2x plus sine x plus 7. Now here's the characteristic on an explicit function of x. Notice f of x is just another symbol for y. So on one side of the equation we have y isolated. Everything on the other side of the equation simply involves constants and x's, functions of x here, but we do not have a mix of the variables. Now let's compare that to what we mean by implicit functions of x. Let's look at this first one. X cubed plus 2xy squared minus 3y plus 4 equals 0. You'll notice over here on this side we have a mixture of our x's and y's. Now you might say, well, perhaps we could rearrange this and solve for y. You might take the x cubed over to the other side and the 4 over to the other side, but notice you have two terms left that involve y. One of them, y is squared, and the other one was y is not. So even factoring out a y would leave another y embedded in there. This would be very difficult to isolate y on one side of the equation. So we call this an implicit function of x. Y is still a function of x here, but it's implicitly defined. Here's another one, 5xy minus y equals 3x. Okay, now on this one, you could factor out the y and divide and write it in an explicit format. But in the form that it's in, it's written in what we call an implicit form. Now, having looked at what we mean as far as the difference between explicit and implicit functions, we're going to talk a little bit about finding the derivatives of these implicit type functions, where it either would be very difficult or even sometimes impossible for us to isolate y on one side. Before we're ready to do that, though, I want to talk a little bit again about notation and exactly what some of these notations mean. So first I've said, what does it mean when you say dy dx? This of course means the derivative of y with respect to x. That means y is a function of x. What does dx dy mean? Well, this is finding the derivative of x with respect to y. It's implying x is a function of y. So basically here, your x's and y have switched roles in terms of which is the independent and dependent variable. And then notice, so what does dv dt mean? I'm just using different variables here. This means the derivative of v with respect to t. So in other words, v is a function of t. Now, I wanted to put this in here because we do things like maybe v stands for volume and t stands for time, and these letters are more convenient. The thing that I want you to notice here is that the denominator in every instance is telling you which variable you are taking the derivative with respect to. Now, I also wanted to put up these examples. What is dx dx? The derivative of x with respect to x. What is dy dy? The derivative of y with respect to y. What is dt dt? The derivative of t with respect to t. You'll notice the thing these all have in common is you have the same variable on both the numerator and denominator. You might recall that you had a formula, the derivative with respect to x of x is 1. The same thing will happen here, and the same thing will happen here. And of course, it's just kind of like you learned early with fractions. If the numerator and denominator looks alike, that's 1, isn't it? Anytime you take the derivative of a variable with respect to itself, you always get 1. Now, with these things in mind, I want to emphasize you must think chain rule when finding derivatives implicitly. All the time be thinking chain rule. Now, what exactly do I mean by chain rule? Well, you might remember when you do the chain rule, like on a general power form, you do the power rule part, and then the chain rule says that you go inside those parentheses and take the derivative of the function that was raised to a power. Or in the case of trig functions, maybe the argument was complicated and you took the derivative of the argument. So we're going to think that same thing, keeping in mind these ideas of notation. Now, let's look at some comparisons. What is the derivative with respect to x of x to the fifth? You'll notice that the variable we're taking the derivative with respect to is the variable that's here. Now, you're used to doing this. You're saying the derivative of x to the fifth is 5x to the fourth. But I want to emphasize here what I meant by thinking chain rule. X is what is raised to a power. Now, your power rule says you bring the 5 down, whatever is to a power you write down and reduce the exponent 1. And then remember, the chain rule said take the derivative of the thing that was raised to a power. Well, basically what you would be looking at there is a 1, because if you're taking the derivative with respect to x, the derivative of x with respect to x is a 1. And of course 5x to the fourth times 1 is the 5x to the fourth that you were used to. Because we started out always sort of taking the derivative with respect to x and working with these, we really didn't ever have to think about chain rule unless this became complicated. But I want you to compare this to this one. I want the derivative with respect to x of y to the fifth. Now, this is a power format just like this one is. So your power rule says bring the exponent down, whatever is to the power you write down, and you reduce it by 1. And then you multiply by the derivative of this thing that is to a power. Now this time, what's to a power is y. I need the derivative of y with respect to x. Well, the way I'm going to indicate that is to put dy dx, the derivative of y with respect to x. I did the power, and then I took the derivative of this thing. Do you see the difference? The derivative of x with respect to x is a 1. But the derivative of y with respect to x we indicate by dy dx. You're going to find this thing creeping into a lot of these problems when we're doing the derivative implicitly. Now, let's look at another example. Find the derivative with respect to x of x squared minus 3y, and you'll notice here we're going to do the same thing except we're doing derivative with respect to y. It's the same function. I want you to just understand the difference here. If I'm doing the derivative with respect to x, when I get to this first term, I do the power rule, get 2 times x. The derivative of x with respect to x is a 1, so I don't have to write that down. Then minus. If you have a constant times a function, you do the constant, and then you take the derivative of the function. Since we're doing this with respect to x, I need the derivative of y with respect to x there. Okay? Now here, I'm doing the derivative with respect to not x, but y. So when I do this first, when I do the power, and then the derivative of this thing that was raised to a power, since I'm doing it with respect to y, I would have to say dx dy. Did the power, 2x, the derivative of x with respect to y, minus, I'll bring down the 3, and the derivative of y with respect to y is a 1. I'm going to put the 1 down for emphasis. So do you see the difference? Depending on which variable you're taking the derivative with respect to. But you notice how I'm doing chain rule every time. Power rule, and then I take the derivative of what was raised to a power. Okay? Now here's another simple one I want us to look at. We're doing the derivative with respect to x of x cubed y squared. Now I want to emphasize here, when you say x cubed y squared, what you really mean is x cubed what? Times y squared. Since that is times, this is indicating I have a product. Notice it's a product of 2 functions. I've got variables both places. So I'm going to need to use the product rule. Okay? And keep in mind I'm doing the derivative with respect to x. Okay, so let's start. Product rule says first function, x cubed, times the derivative of the second function. Now this is a power, so 2y, chain rule, the derivative of this is dy dx. You see I'm taking the derivative of y with respect to x, okay? Plus first derivative of second plus the second function y squared times the derivative of the first function, 3x squared, and when you think chain rule here, the derivative of x with respect to x is a 1. I'm going to put the 1 down for emphasis here. I want you to understand why the dy dx is here and you just have a 1 here. It's because we're doing the derivative with respect to x. Product rule first, derivative of second. This is a power, so do the power rule and then chain rule, derivative of that. Then second function, derivative of first. This is a power. Do the power and then chain rule, derivative of that. Turns out to be a 1. Now I'm going to rewrite this as 2x cubed y times dy dx plus 3x squared y squared. Okay? Now that we've looked at sort of the basics, let's look at an equation. Notice I want to find dy dx of 3y to the 5th plus 2y cubed minus 8y plus 5x squared plus 2 equals 0. Now, we're just going to move through this term by term using the addition rule for taking derivatives and keeping in mind chain rule and what I'm taking the derivative with respect to. So looking at my first term here, I just have a constant times this power. So when I do the power rule, 5 comes down, I have 5 times 3 is 15, and then I will drop that down a power, y to the 4th, and then think chain rule. The derivative of this will have to be dy dx, because I'm taking the derivative with respect to x, so it's not a 1. Okay, plus, I've got a power format here. 3 times 2, I get 6. I'll drop down a power, so 6y squared, again, the derivative of what's raised to a power using chain rule, dy dx. Okay, moving to the next term, minus, I have a constant times y, so I bring down the constant, and the derivative of the y is dy dx. Move to the next term. This is a power. 2 times 5 is 10. X to the first power. When I take the derivative of that with respect to x, I get a 1. Now, you don't have to write those 1s, but I'm putting those down for emphasis so that you understand why you have a dy dx sometimes and sometimes you don't. Okay, the next term is a constant. The derivative of a constant is 0 equals the derivative of the constant 0 is a 0. Okay, now we have completed the derivative, but you'll notice it's in an implicit format. We will be able to solve for dy dx. So what I want us to do, notice these first 3 terms all have dy dx in them, and this term here does not. So the first thing I'm going to do is to rewrite this as 15y to the 4th times dy dx plus 6y squared times dy dx minus 8 times dy dx equals, and I'm going to move this term to the other side of the equation. So I'll subtract the 10x and move it over there. Notice I can just ignore the zeros. Now I've got all of the dy dx's isolated on this side, so now I can factor out the dy dx. So I'm going to factor that out. That will leave me 15y to the 4th plus 6y squared minus 8 equals the negative 10x. Now since dy dx is times all of this, if I divide by this quantity, I'll get dy dx by itself. So dy dx will equal the negative 10x divided by 15y to the 4th plus 6y squared minus 8. Now you'll notice that I was able to solve for dy dx, but you'll notice over here it's sort of in an implicit format in the sense that my x's and y's are all mixed together, kind of like they were up here in the original function. Okay, I put some guidelines. Differentiate with respect to x. Collect all terms containing dy dx on one side of the equation. Other terms that do not have that dy dx go to the other side. Factor out your dy dx and then solve. Okay? Alright, we want to find dy dx. Our function is 5x squared plus 2y squared minus 7xy plus 4x minus 3y equals 9. Again, we're going to move from term to term to do this derivative, and remember we're doing the derivative with respect to x. Okay, so I have a power here. 2 times 5 is 10. X to the first power, the derivative of x with respect to x is a 1. I'm not going to write the 1 this time. Plus, I have a power format here. 2 times 2 is 4. Y to the first power, the derivative of that y is dy dx. Now, when we get to this next term, be careful. See that thing right there? x times y. I have a product here. See, two different variables, but they're multiplied. So I'm going to have to think product rule for this term. Now, I found the easiest way for me is I'm going to bring down this constant, -7, and I'm going to use a parenthesis. And I'll do the product rule for my x times y. Okay, so my product rule says first function x times the derivative of the second one is dy dx, plus the second function is y, and the derivative of the first function is 1. I'll put the 1 down this time for emphasis. Do you see how we did the product rule on that x times y? Okay, we're going to move to the next term. Plus, bring down the constant 4. The derivative of x with respect to x is a 1, so I'm just going to leave that at 4. Minus, we'll bring down the 3, and the derivative of y is dy dx, equals, this is a constant, the derivative of a constant is 0. So, did you follow through? Just power rule here, the derivative of x with respect to x is a 1. Power rule, but the derivative of y with respect to x is needed. We brought down the constant, we did product rule. First, derivative of second, plus second, derivative of first. Constant times a function, but the derivative of x with respect to x was a 1. Brought down the constant, derivative of y with respect to x equals the 0. Now, again, we're ready to do some simplifying. So, first of all, I'm going to notice that I've got some dy dx's scattered here and there, but I've got this parenthesis here, so I'm going to need to distribute this -7 here. So I think what I'm going to do, I'm going to go ahead, I see this 10x here that's by itself that does not have a dy dx, and I see this plus 4 that doesn't. I'm going to go ahead and move those to the other side as I rewrite these other terms. 4y dy dx. I'm bringing that one down. I'm going to distribute my 7. -7x dy dx. And then notice you have a -7y. And then I'm going to bring down the -3 dy dx equals, I'm going to go ahead and move this, so subtract 10x, and I'm going to move this one, subtract 4. Now make sure you don't lose any terms. We took that to the other side. We brought this one down. This one is here. This one is here. We took the 4 over. This one is here. Now you'll notice I have this term that does not involve dy dx. So I'm going to move it over here. Okay? So 4y dy dx minus 7x dy dx minus 3 dy dx. I'll add the 7y, so 7y, and bring down the minus 10x minus 4. Now we're ready to factor out the dy dx on this side, leaving 4y minus 7x minus 3. I'll go ahead and recopy the right-hand side. Now, since dy dx is times this quantity, we're going to divide to solve for dy dx. So dy dx is going to equal 7y minus 10x minus 4 divided by 4y minus 7x minus 3. Now, I might mention while I have this example up here that I have chosen in both of these last examples to isolate the dy dx's on this left-hand side of the equation and take everything else to the right. There's certainly nothing wrong if you wanted to take all the dy dx's to this other side over here and bring these terms. What happens in that case is that your signs are all reversed. So if you did that, you'd get your dy dx on this side. This would be -7y plus 10x plus 4. This would be -4y plus 7x plus 3. I mention that because sometimes my students think they have a wrong answer when maybe they went to an opposite side of the equation. If you're ever checking answers and you're not sure if yours doesn't look exactly like the one in the back of the book, if you're comparing it with that one, if all of your signs on this are exactly opposite the signs of the answer in the text, then you do have the right answer. You just went to a different side of the equation to solve. Okay, well here's one that involves some trig functions. Find dy dx. We have 2 times the sine of y plus 5 times the cosine of x equals 4. Now, we're again going to work on this derivative implicitly. So we'll move from term to term. So here I have a constant times this function. We'll bring the constant down. This is a sine function. The derivative of sine is cosine. Remember, the argument stays the same. But then chain rule, we take the derivative of the argument, and since we're doing the derivative with respect to x, we need to write dy dx there. Okay? Plus, we have another constant times this function. Okay, so we'll bring the constant down. This is a cosine function. The derivative of a cosine is negative sine, same argument, so negative sine x. The derivative of this argument would be a what? 1, because the derivative of x with respect to x is 1. Equals, the derivative of a constant is 0. So I have 2 times the cosine of y times dy dx equals negative 5 sine, not equals. Let me kind of erase that. Minus 5 sine x, there we go, equals 0. Now, this term does not have dy dx in it, so we're going to move it to the other side. 2 cosine y dy dx would equal positive 5 sine x when we add and take it to the other side. And then, since 2 cosine y is times dy dx, we'll divide by that. Dy dx will equal 5 sine x divided by 2 times the cosine of y. Find the derivative with respect to x of tangent xy equals 4x minus 3y. Okay, well, this is a tangent function. What's the derivative of a tangent? Secant squared, isn't it? So, secant squared, and remember the argument stays the same, xy. Chain rule then says take the derivative of this argument. Now be really careful here. xy means what? X times y. We're going to need to do a product rule here on this argument. First is x times the derivative of the second, dy dx, plus the second function y times the derivative of the first is 1. The derivative of x with respect to x is 1. Okay, so we did the derivative of tangent is secant squared, same argument. Chain rule says take the derivative of this argument, but that was a product, so we had to do product rule. First derivative of second plus second derivative of first. Okay? Alright, on the other side, we've got a constant 4. The derivative of x with respect to x is a 1. And then minus 3, the derivative of y is the derivative of y with respect to x. Okay? Now, let's distribute this secant squared here. I've got x times secant squared xy times dy dx plus y times secant squared xy, and on this side I have 4 minus 3 times dy dx. Now this time you'll notice this term and this term have the dy dx. This and they're on opposite sides of the equal. So we're going to bring this one over here with this one, and then this that does not have dy dx will move over here. So x secant squared xy times dy dx. We'll add this, so plus 3 times dy dx equals, now the 4 is still over here, but we're going to subtract this y secant squared xy. So we have all the dy dx's on the same side. Now we can factor out the dy dx, leaving x secant squared xy plus 3. And I'll recopy the right-hand side here. And then again, we'll divide by this quantity to finish solving for dy dx. So our answer will be 4 minus y times secant squared xy over x secant squared xy plus 3. I hope that you're beginning to get the hang of this idea of doing the derivative implicitly and thinking chain rule. Okay, well, let's take a look at this one. Find the derivative with respect to x. 3xy plus 7 quantity squared equals 6 times y. Now notice here, this is a quantity squared. So on this side we've got a power format, don't we? So we're going to do power rule. That means we're going to bring the 2 down. We'll recopy this function, 3xy plus 7. We'll reduce the exponent, and that will become a 1. And then we're going to think chain rule times the derivative of the stuff inside here. Okay? Now, this time, just to make this a little easier, I'm going to consider 3x to be the first function and y to be the second, and this is a product of 3x times y. Okay? So my first function, 3x, times the derivative of the y is dy dx, plus the second function y times the derivative of the first function 3x would be a 3 times 1. Of course, the derivative of that 7 is a 0. Okay, so I did the power. 2 came down, my quantity reduced to the first power, and then I went inside. This was a product. So first, derivative of second, plus second, derivative of first. Okay, equals. Now on this side we've got 6 times the derivative of y is dy dx. Okay? Alright, now notice all of this is times the stuff in brackets. So 2 times 3xy plus 7 times 3x is all times dx dy. Or sorry, dy dx. So 2 times 3x, I have a 6x times 3xy plus 7 all times dy dx. Plus, I have a 3y times 2 times 3xy plus 7. So it's going to be a 6y times the quantity 3xy plus 7 equals 6 times dy dx. Okay? Let you look that over, make sure you see where everything came from. Now, I've got dy dx here and dy dx here, and this does not have a dy dx. So I think this time, since this has dy dx, I'm going to subtract this one, bring it over here with that one, and leave this 6y times 3xy plus 7 over here by itself. 6 dy dx, subtract 6x times 3xy plus 7 times dy dx. Now, there's several things I could do to factor, but remember the objective is to solve for dy dx. So, first of all, I'm just going to recopy this left-hand side, and I'm just going to factor out dy dx on this side. So I'll have 6 minus 6x times 3xy plus 7. Okay? And to finish solving for dy dx, we just need to divide by this. 6y times 3xy plus 7 is divided by 6 minus 6x times 3xy plus 7. Now, at this point, you could leave your answer in this format if you want to. The other thing, of course, that you could do is you've got a 6 here. If you wanted to factor out a 6 and cancel with this 6 here, we might at least do that. Let me get another little sheet of paper here so we've got room to show you that. So we could leave 6y, 3xy plus 7 up here, and if I factor the 6 out of these two terms, it leaves 1 minus x times the quantity 3xy plus 7. And since the 6 is times everything in this 6, we could cancel those 6's. Okay? Now, also, again, some of these things are optional. I just want to show you some options here. If we leave this numerator factored like it is, in the denominator now, what you might want to do is go ahead and distribute that x. 1 minus 3x squared y minus 7x. That just makes it look a little more simple without so many parentheses. Again, there's, I guess it's at least good to get that 6 out of there and get that reduced, whether you do anything else to the rest of this or not. But I wanted to show you some options because sometimes those do look a little different. Keep in mind, again, I want to come back up here where I chose to take all the dy dx's to this side. Just keep in mind, if I had brought them over here, this would have stayed positive and I would have had a minus 6, and this would have come over as a negative 6. That's the reason that all your signs would be just exactly opposite. So if you did this problem and you took the dy dx's to the left, you might have a positive here, a negative here, and a negative here. and it would be the same answer, but just in a different format. Now that we have had some practice in finding the derivative implicitly, we're going to look at some problems where we apply using this implicit derivative. I might want to remind you that one of the applications that you had with derivatives was that it would give you slope of a graph at a point, and the way we defined slope of a graph was we said the slope of a graph is basically defined as the slope of the tangent line at a certain point for that graph, and we use the derivative to find the slope of that tangent line. Let's look at an example. Find the slope of the curve x squared plus y squared equals 9 at the point 1, 2 times the square root of 2, and also at 1, negative 2 times the square root of 2. Now, I've got a little graph thing here. You might recall x squared plus y squared equals 9 is what? It's just a circle, center at the origin, radius of what? Square root of 9 is 3. So I'm just going to kind of do a rough sketch here. Centered at the origin, radius 3. And my circle's not going to be perfect, but will at least give us some idea of what we're talking about here. Okay, so we've got this circle. Notice if x is 1, would be at 2 square root of 2, roughly right in here. And also when x is 1, we've got another point down here, negative 2 times the square root of 2. And of course you can check that. If x is a 1, you get a 1 squared. Subtract that from 9, you get an 8. So y squared would be 8. So if y squared equals 8, then y is plus or minus the square root of 8. And of course you can simplify the square root of 8 and get that 2 square root of 2. That's the reason we have the 2 points. Okay? Now, you would have a tangent line at the curve here, and you would have another tangent line to the curve here. So we want to find the slopes of these tangent lines, basically. Now, the way we're going to do this is we're going to find dy dx, because dy dx gives us slope of tangent lines. Yeah, I just used an m there for slope. Okay, so look at your curve. So if we take the derivative of the first term, we're going to do this with respect to x. We do the power rule 2x. Derivative of x with respect to x is a 1, plus, do the power rule here, 2 times y, and then chain rule, so dy dx equals the derivative of 9 is a 0, since it's a constant. Now, we can subtract the 2x. So I have 2y times dy dx equals negative 2x. We'll divide by the 2y. So dy dx equals negative 2x divided by 2y. We can cancel the 2's, and we get negative x over y. Okay? Now, notice at the point 1, 2, square root 2. This is x, and this is y. So the slope would be the negative of x, so that'd be negative 1, over the y, 2, square root 2. Okay? At the point, let's see if I have room for this, 1, negative 2, square root 2, my slope would be the negative of x, negative 1, over the y, negative 2, square root 2, and of course a negative divided by a negative is a positive. Notice at the point 1, 2, square root 2, we got a negative slope, and that's consistent with the way our tangent line is sloping down, isn't it? At the point 1, negative 2, square root 2, we got a positive slope, which again is consistent with the way that this line is sloping. So we can take a function that's written in the implicit format, find the derivative implicitly, solve for dy dx, and we can still apply this as being the slope of a tangent line, which means the slope of the curve, basically, at that point. Okay, here I've said find the equation of the line tangent to the graph of x squared minus xy plus y squared equals 7 at the point negative 1, 2. Now I'm not going to graph this one, but we're just going to go ahead and go about finding the equation of the tangent line. Now if you want the equation of a line, y minus y1 equals m times x minus x1. You have to know the slope and a point. Well, we do know the point. So I'm going to go ahead and fill that in. It'd be y minus 2 equals m times x minus a negative 1, or x plus 1. So what we lack is knowing the slope. Well, we get the slope from the derivative, don't we? So we're going to find dy dx. Okay, so starting here, the derivative of x squared is 2x. Chain rule, derivative of x with respect to x is 1. Now be careful. See this xy again? That's a product, isn't it? Now with that negative there, I'm going to encourage us to be careful. Let's put the negative down, then we don't have to worry about the negative. We're just going to do the product rule here. First function x times the derivative of the second one would be dy dx, plus the second function y times the derivative of the first one, derivative of x with respect to x is a 1. Okay? Plus the derivative of y squared, do your power, 2 times y the first power. Chain rule, derivative of y is dy dx. And of course on the other side the derivative of a constant is 0. Now, if we distribute our negative here, we have 2x minus x dy dx minus y plus 2y dy dx equals 0. Here's my dy dx terms, so let's isolate those. Negative x times dy dx plus 2y times dy dx equals, we're going to move this and this to the other side. So since we're adding the y, let's put it first and then subtracting 2x, so y minus 2x. Now I'm going to factor out my dy dx, which leaves minus x plus 2y. And then we divide. So dy dx equals y minus 2x. And I think I'm just going to write this in the form 2y minus x instead of saying minus x plus 2y. It's the same difference. Now, this is going to give me slope, isn't it? Now, notice this involves both x and y, but I know both x and y at the point in question. So y is a 2. So I'm going to have a 2 here. Minus 2 times my x is negative 1 over 2 times y, well 2 times 2 then, minus my x of negative 1. Okay, so this is going to be 2 plus 2 is 4, and this is going to be 4 plus 1 is 5. So my slope at the point, negative 1, 2, is 4/5. We're going to bring that up to our equation here. Y minus 2 equals 4/5 times x plus 1. I think I'm just going to go ahead and put this in slope-intercept form. So I'll distribute the 4/5. So 4/5 x plus 4/5. Now I'm going to add the 2. So y equals 4/5 x. And since I'm adding it to this, adding 2, 2 is 10/5. So that would be 14/5 when I add them together. So this would be the equation of the tangent line at the point negative 1, 2. Okay, find y prime for cosine y equals x. Now, since this is involving x and y, we're going to assume y prime here means dy dx. Okay? Well, I have a trig function here. What's the derivative of cosine? Derivative of cosine is negative sine. Remember, argument stays the same. And then chain rule, the derivative of the argument, dy dx, equals the derivative of x with respect to x is 1. So dy dx equals 1 divided by negative sine y. Now, you might be saying, well, why are we doing that? That seems really simple. Well, what we're going to do here is do a little bit of rewriting and show you something rather interesting. First of all, if you have a positive divided by a negative, it doesn't matter where you put that negative. So I'm going to write this as negative 1 over sine y like that. Now, recall from trig, you have an identity. Cosine squared y plus sine squared y equals what? 1. Since the cosine of y is x, cosine squared y would be x squared. So x squared plus sine squared y equals 1. Sine squared y then equals 1 minus x squared. And so the sine of y would be either plus or minus the square root of of 1 minus x squared. Okay? Now, I can replace this then in this formula. dy dx equals negative 1 over plus or minus the square root of 1 minus x squared. Now, you might say, well, how do you know whether to use the plus or the minus? Well, you're going to need to be given some information about what quadrant y would be in order to make that designation here. If you restrict yourself to quadrant 1, then you know all the trig functions are positive there, so you would choose your plus sign, and your derivative would be negative 1 over the positive square root of 1 minus x squared. The interesting thing here is, notice in this format we have the derivative in terms of y, but using some trigonometry we can change that where we get the derivative just in terms of x. Okay, now we're going to go to looking at some second derivatives. Do you recall this notation? Notice if the 2's written between the d and the y, it's saying find the second derivative of y. And here the 2's written after the x because you're indicating you're doing the derivative with respect to x both times. Second derivative of y with respect to x both times. Okay? Well, to get a second derivative, we do what? We need a first derivative, don't we? So we're going to start with the first derivative. Okay, starting here, the derivative of 3x squared, we'll use the power form, 6x to the first power. The derivative of x with respect to x is 1, plus, power rule here, 4y to the first power, and then the derivative of y with respect to x, equals the derivative of 6 is 0, since that's a constant. Now we're going to solve for dy dx. So 4y times dy dx would equal negative 6x, and then we'll divide. Dy dx equals negative 6x over 4y. Now I can do a little reducing here. We can divide by 2's, numerator and denominator, negative 3x over 2y. Now that we have the first derivative, we're going to get the second derivative. If this is dy dx, then we just take the derivative with respect to x of this solution. Now this is a quotient. I can't spell Q-U-O-T-I-E-N-T, quotient. So we're going to have to think quotient rule. Okay, denominator is 2y times the derivative of the numerator, negative 3 times 1, because we're doing the derivative with respect to x again, minus the numerator, negative 3x, times the derivative of the denominator. Well, that's 2. The derivative of y is dy dx. This is all over the denominator squared, 4y squared. Okay, let's run through that. Again, we got our first derivative. That was pretty simple. This is a quotient. So to get the second derivative, we're applying the quotient rule. Denominator, derivative of numerator, minus numerator, derivative of denominator. Notice we have to put that dy dx in, over denominator squared. Now we're going to need to do some simplifying. So let's take this a little at a time. The first thing I'm going to do is just kind of clean it up a little bit like we've done in some of the other examples. So let's rewrite second derivative of y with respect to x the second time. This is just negative 6y. And then a negative times a negative, we're going to get a positive 6x times dy dx over 4y squared. Okay? Now, notice right here where you've got dy dx, we know that dy dx is negative 3x over 2y. So we're going to substitute that in. So negative 6y plus 6x times the quantity, negative 3x over 2y. And then all of this is over 4y squared. You see what we did? We just substituted dy dx is this, so we substituted for it here. Okay? Now, let's keep doing a little simplifying here. So we have negative 6y. This will end up being a negative 18x squared over 2y. All of this over 4y squared. Now, I'm going to clear out my complex fraction. So I'm going to multiply the numerator and denominator by 2y. Okay? So 2y times negative 6y is a negative 12y squared. And then here the 2y's will cancel, so minus 18x squared. And 2y times 4y squared is going to be an 8y cubed. Okay? Now, we can do just a little bit of reducing here. Between the negative 12 and the negative 18, we have a common factor of negative 6, don't we? So let's pull that out. We'll have a 2y squared plus 3x squared. This is over 8y cubed. Now, we can reduce the 6 and the 8. So we'll divide those by 2. Negative 3 times 2y squared plus 3x squared over 4y cubed. Notice, as we did this second derivative, we had a dy dx. But because we had dy dx up here, we can always replace that and get rid of that term. And then we may need to do some simplifying, but we can get down to a format where we have the second derivative of y with respect to x. Although it's implicit, at least it does not involve that first derivative any longer. Example that I would like to do for you involving finding a second derivative. Notice this says find y double prime for xy plus y squared equals 1 at the point 0, negative 1. So here, not only do we want to find that second derivative, but we want to evaluate it at a given point. Okay, so just like before, we're going to start with the first derivative. Now, notice we have a product again here. First, x times the derivative of the second one, dy dx, plus the second function y times the derivative of the first one is a 1. We've done our product. Plus the derivative of y squared, we'll use the power, 2y, and then the derivative using chain rule, dy dx, equals 0. Now, I have these two terms involving dy dx, so I'm going to subtract that y and take it to the other side. X times dy dx plus 2y times dy dx will equal negative y. We'll factor out dy dx, leaving x plus 2y, and then finally we'll divide dy dx equals negative y divided by x plus 2y. Okay, so we have our first derivative. Now, as we did before, we're going to start on the second derivative, again taking the derivative with respect to x. So I'm going to use this notation to emphasize again, we're taking the derivative with respect to x. Now, keep in mind here we have a quotient, don't we? So, quotient rule. Denominator, x plus 2y. The derivative of the numerator is negative dy dx. Okay, denominator times the derivative of the numerator minus the numerator, so minus a negative y, times the derivative of the denominator. Okay, the derivative down here is 1 plus 2 times dy dx. This is over the denominator squared. Okay, let's just take a pause here and go through this and make sure we have everything accounted for here. We have the denominator, x plus 2y, times the derivative of the numerator, minus dy dx, then minus the numerator times the derivative of the denominator over denominator squared. Now, as we've always done before, let's do a little bit of cleaning up on this so that we can get it simplified. So, first of all, let me rewrite this second derivative of y with respect to x here. Okay, I'm going to distribute this negative dy dx across these terms. So I have minus x times dy dx, and then minus 2y times dy dx. Notice this is going to be a plus y times 1, so plus y, and then a plus y times the 2 is a plus 2y times dy dx, all of this, again, is over x plus 2y quantity squared. Now, notice I have a minus 2 dy dx and a plus 2y dy dx. So those terms will add to 0. That's going to help us out considerably here. So let me recopy what we have again. We have a minus x times dy dx plus y. This is over x plus 2y quantity squared. Okay? Now, remember how we substituted for the dy dx? So let's put down our minus x, and we're going to replace dy dx. Remember, up here dy dx was a minus y over x plus 2y. So let's put that in, a minus y over x plus 2y. So I have my minus x times my dy dx plus y. All of this is over x plus 2y quantity squared. I'm going to go ahead and simplify a little bit more. I'm going to get rid of this fraction. So I'm going to multiply the numerator and denominator of my fraction here by x plus 2y. Now notice x plus 2y times this, the x plus 2y's cancel, and I have a negative x times a negative y is a positive x times y. And then I'll have a plus the y times the x plus 2y. And then x plus 2y squared times x plus 2y makes x plus 2y cubed. Okay? Notice here, if I distribute my y, I have xy plus yx plus 2y squared over x plus 2y quantity cubed. These are really the same term, aren't they? X, y, and yx is the same thing, so I'm going to go ahead and combine those. I have 2xy plus 2y squared over x plus 2y quantity cubed. Now I'm going to stop at that point as far as simplifying. That's a good form if I just want that second derivative. But I want to go back now and remember that we want this value of the second derivative at the point 0, negative 1. So let me just make a note here at the point 0, negative 1. This is x and y, and we're going to substitute that in here. So I will have 2 times 0 times negative 1 plus 2 times negative 1 squared. And in the denominator, I'm going to have a 0 plus 2 times negative 1 quantity cubed. Of course, 2 times 0 times negative 1 is a 0. Negative 1 squared is 1 times 2 gives me a 2. And this is a 0. 2 times negative 1 is negative 2. And if I cube negative 2, I get negative 8. And that will reduce to negative 1/4. I hope that having seen all of these examples, you're having a little bit easier time in understanding how to do an implicit derivative. Just remember, as I said earlier, you've got to think about that chain rule and also keep in mind, what are you taking the derivative with respect to? This completes the lesson on implicit differentiation.